Hi student, now I'll talk about the acceleration, which is section point 2.3, which is in page 40. Okay, now let us imagine this experiment. We have a car toy, and this toy is sliding over this incline. Okay, at t equals 0, the car was here. After 1 second, it was here. It moves this distance. After 1 second, at t equal 2, it will be here. This distance is more than this one because its velocity increases. We know that if we throw a body as a free fall, we will see that it will accelerate. We are talking about the acceleration, which is the change in velocity with respect to time. We have the motion in this direction in this experiment. The direction of motion is with a slope of theta of that incline. We can make it horizontal to study this problem. So I make it horizontal and I name it x direction. It's okay. I can take this xy plane and I can rotate it as I like. The motion of the car is perpendicular in the direction of x direction. Now, this is my system. I understand it now. This is the first step. The initial point, the original point, is at x equal to 0, at time equal 0. This is the first point. After one period of time, which is 1 second, the car was at x equal to half meter. The unit of distance here is meter. After 2 seconds, the car moves more distance than before. It is at x equal 1.3. The distance is more. After, for example, if we need to go more, after at t equal 3, at the fourth position, the x position is 3 meters. We know that we have change in time, we have change in position. In this case, we have velocity. So we have velocity in the first period, which is v1. I name it v1. I can name it v average 1. We have in the second period, second velocity, second average velocity. We have in the third period, third average velocity. We have all the variables or the parameters which are the positions x and the t's to calculate the velocities. It's easy. We can find v1 as we learned before. It is delta x over delta t in the first period. Delta x, x2 minus x1, which is half minus 0, over t2 minus t1, which is 1 minus 0, which is half meter per second. Here the units is meter and the units in the denominator is second. This is the first average velocity. The second average velocity, it is x3 minus x2 over t3 minus t2. It will be 1.3 minus half over 2 minus 1. It will be 0.8 meter per second. The velocity now is more than the velocity before. That means the velocity changes its magnitude. This means we have acceleration. Let us see the third one. The third velocity is x4 minus x3 over t4 minus t3, which is 3 minus 1.3 over 1 second it will be 1.7 meter per second. Also, the velocity, the average velocity here is more and more. Okay, when we have change in velocity, then we have acceleration. This is the mean of acceleration. Sometimes that change will be in positive direction, sometimes in negative direction, and we have positive acceleration and negative acceleration. We will see that in the examples. Now this is our problem. This is it. We have the positions again and again, and the velocities. We have a change as we compute a change in position with respect to time, and we find the average velocities. We can also calculate the acceleration, which is the rate of change. The acceleration is the rate of change of velocities with respect to time. It is easy. It is the same steps. The acceleration is delta v over delta t. The velocity is delta x over delta t. But now we have delta v over delta t. We have another step, which is v final minus v initial over t final minus t initial. Okay? The instantaneous acceleration, again and again, it is the same as average acceleration, but when delta d goes to 0. So it will be not delta v over delta t, it will be dv over dt. It is the derivative of the velocity with respect to time. It will be easy, you will see that. Okay, let us compute now the first acceleration in the first periods and the next acceleration, a1 and a2. a1 is delta v, which is v2 minus v1 over t2 minus t1. So v2 minus v1, v2 we computed it as, this is v2 0.8 minus v1 0.5 over the time period. The first period from 0 to 1, the second period from 1 to 2. We will take the average between them. So we will take this at a half second, or we will take 1 second, 2 seconds, and the change of them is, the change of this period is 1 second. Okay? If we take the end of that period, 2 minus 1, so it will be 0.8 minus half, it will be 0.3 over 1. The denominator is meters per second, it is velocity. The denominator is in seconds, which is time. So we have meter over second over second. Of course, the value is 0.3 meter per squared second, because we have here a second and here another second. What about the other acceleration value between? What is the rate of change of velocity in the second stage? It is v3 minus v2 over t3 minus t2. We can put the units at each value, or we can put them at the end of the expression. Okay, the velocity v3, we computed it, is 1.7. v2 is 8, 0.8. The change of time is 1 second. Then the acceleration will be 0.9 meter per squared second. This is the average acceleration between different periods. What about the instantaneous acceleration? It is the same as instantaneous velocity. It will be easy. We know from before that we may have x as a function of t. Then we can find v of t. Then we can find a of t, because a is the derivative of the v with respect to t. If we have a function of t, which is x is equal to 3 t to the 4 minus 2 t cubed plus t plus 5, it's an arbitrary function. Then the velocity as a function of t is the derivative of the position with respect to t, which is 12. If we derive this function, it will be 12t cubed minus 6t squared plus 1, and the derivation of 5 is 0. And the acceleration is the derivative of the velocity, but the velocity is the derivative of x. So the acceleration is the second derivative of x with respect to t, which is d2x by d squared. Okay, you need to derive the x of t, the position function, 2 times to reach the acceleration as a function of t. In this case, we can find any instantaneous position or velocity or acceleration as a function of time at any time. You can solve x of t is equal to 7 at t equals 7. We can find it. We can find x at t equal to v at equal to t equal to. We find the acceleration at t equal 1. It is easy. Just put 1 at in place of t. 36 multiplied by 1 squared minus 12 multiplied by 1, it will be 24 meter per squared second. Look at here. A at x is equal to 5. It's okay. When x equal to 5, when t equal to 0, this is 0, and this is 0, and this is 0. So when we put the acceleration at t equal to 0, it will be 0. It is easy to find the magnitude or the value of a function if you have the independent value of that function. You will see more example about this subject. Thank you.